Hello students, today we see the uh, chapter on helical and bevel gear. We take the revision of this unit. So here we discuss about the helical gear design. For that purpose we first see the terminology in case of helical gear. So in this figure, if we observe the helical gear from the top portion, then we see the teeth in inclined direction. If we take the two planes which shows with TT line and second plane, that is NN, which is perpendicular to the inclined direction. So this NN plane is called as normal plane and this TT plane is called as transverse plane. If we observe the normal plane, if we observe the helical gear, then we see this type of shape, and this shape is same like spur gear. This profile is like involute profile in similar to spur gear. So if we see here in transverse plane, that is if we consider this is TT plane, that is transverse plane, and if we observe from this direction, then we see this type of profile. Now we discuss about the terminology. So if we see the first term, that is helix angle. Helix angle is indicated with symbol psi. Helix angle is an angle made by the helix with the axis of rotation, or it is an angle made by teeth with the axis of rotation. So if we observe this diagram, then this is the helix and this line is parallel to the axis of gear. So angle between these two lines is indicated with symbol psi, and this angle is called as helix angle. Second term is transverse circular pitch or PT and transverse module, that is MT. Circular pitch measured in the transverse plane is called transverse circular pitch. So if we observe this diagram again, then the distance between two corresponding teeth in transverse plane, this distance is called as transverse pitch. And module in the transverse plane is called transverse module, and that module is indicated with symbol MT. Then PT is equal to pi into pitch circle diameter D divided by number of teeth Z. Transverse module is equal to PT divided by pi, so which is equal to D upon Z. Third point is normal circular pitch, that is PN, and normal module MN. If we see the definition, circular pitch measured in the normal plane is called normal circular pitch, that is PN. And if we observe the diagram again, then if we observe this in a normal plane, and distance between two corresponding teeth is called as this PN, that is normal in normal plane, this is normal circular pitch. And Mn is the normal module, which is equal to Pn upon pi. From figure, AC upon AB is equal to cos psi. If we observe the figure, then in this figure, if we consider this is A point, this is C point, and this is B point. So if we see the formula, then AC upon AB, So if we consider this is AC, this AC distance is equal to this normal pitch distance, and AB is nothing but PT. So AB upon AC upon AB is equal to cos psi, and if we substitute the distances, then Pn upon Pt is equal to cos psi. Therefore Pn is equal to Pt into cos psi. Similarly, Mn is equal to Mt into cos psi. As helical gears are normally generated by hobbing, normal module is a standard and is equal to the module of the hob cutter. So in case of helical gear, these two modules are available, that is normal module and transverse module. So generally normal module is considered as a standard module. And if we see the next important term, that is axial pitch, that is PA. Axial pitch is the distance between the corresponding points on the adjacent teeth measured on the pitch surface in the axial direction. So if we observe the figure, then AB upon AD is equal to tan psi. So here if we draw the straight, that is parallel to the axis of the gear, and if we extend the CB line that intersect this vertical line at D, so this triangle, if we consider, that is AC upon AB, sorry, that is AB upon AD. If we observe here, AB upon AD, so AB is PT distance and AD is PA distance. So AB upon AD is equal to tan psi, therefore PT upon PA is equal to tan psi, and therefore PA is equal to PT upon tan psi. Now next important term is transverse pressure angle, that is indicated with phi t symbol. So pressure angle measured in the transverse plane or plane of rotation is called transverse pressure angle. Normal pressure angle, that is phi n. Pressure angle measured in the normal plane perpendicular to the teeth is called normal pressure angle. So in this diagram, this angle is called as normal pressure angle phi n, and this angle is called as transverse pressure angle. The normal pressure angle and transverse pressure angle are related by the equation, that is tan phi t is equal to tan phi n divided by cos psi. So by using this relation, we can correlate phi t with phi n. Next important term is face width, which is indicated with symbol B. It is the length of the gear tooth measured along a line parallel to the gear axis. And if we see the formula, so B must be greater than or equal to 1.15 into pi into mn upon sin psi. Again, next point is speed ratio or gear ratio, which is indicated with symbol G. G is equal to number of teeth on gear divided by number of teeth on pinion, which is equal to diameter on gear, pitch circle diameter on gear divided by pitch circle diameter on pinion, which is equal to speed of pinion divided by speed on gear. 9 point is center distance, which is indicated with symbol A. Center distance A is equal to dp plus dg upon 2, which is equal to, we know that dp is module into number of teeth, but in this case dp is mt into zp plus mt into zg divided by 2. mt is common in both the terms, so mt we take common in bracket zp plus zg upon 2. Therefore we know the relation between mt and mn, that is mt is equal to mn upon cos psi. In place of mt we substitute mn, So mn upon cos psi into bracket zp plus zg upon 2. Therefore mn upon cos psi into bracket zp plus g into zp divided by 2. So center distance A is equal to mn upon 2 into cos psi into zp, because zp is common and we take 2 outside the bracket. So in bracket 1 plus g. Next point is tooth proportions. That is addendum HI is equal to 1 times normal module. Dedendum HF is equal to 1.25 times normal module. Now, if we consider the helical gear in normal plane, and then we see the tooth is similar like it is like that of spur gear. So we use the same design procedure as discussed in spur gear design, but in this case, because of the inclination of the teeth, we convert our helical gear into equivalent spur gear, and after converting into equivalent spur gear, then we uh, use the same procedure which is discussed for spur gear design, and that is called as equivalent spur gear. So equivalent spur gear and formative or virtual number of teeth. So helical gear is a kinematically equivalent to an imaginary spur gear in a normal plane, that is plane perpendicular to the teeth. This imaginary spur gear in the normal plane, which is kinematically equivalent to the helical gear, is known as equivalent spur gear. Important parameters of equivalent spur gear. Two important parameters are there, that is pitch circle diameter and number of teeth. So pitch circle diameter of equivalent spur gear is indicated with d dash symbol, and d dash is equal to 2 times radius dash, that is r dash, is equal to d upon cos square psi. Here this d is actual pitch circle diameter for helical gear. Then second term is number of teeth on equivalent spur gear, that is z dash. So z dash is equal to z upon cos cube psi, where this z is actual number of teeth on helical gear and z dash is equivalent number of teeth on spur gear. So if we observe these two terms, here we give the dash symbols for equivalent spur gear. Now we can move the next topic in this chapter, that is force analysis of helical gears. If we draw the if we draw the free body diagram of helical gear, then this is the pinion and this is the gear. If we see the side view, then this is the that is pinion side view and this is gear side view. If we consider this is the driven member and this is the driving member, this inclination indicates this gear is right handed, and this type of inclination indicates this is left handed. In case of helical gears, three different types of forces are acting, that is radial force, tangential force and axial force. If we compare this to the spur gear, then here one more force is acting along with tangential and radial force. That extra force in helical gear is axial force. It is also called as thrust force, which is indicated with Fa symbol. If we see the direction for the three forces, then Fr and Ft, this direction is same like in which is discussed in spur gear design. I want to revise again. Fr acts towards the center of respective gear. If we consider top gear, then Fr acts on upward direction. If we consider bottom gear, then Fr shows in downward direction. Then if we mark the direction for tangential force, then observe which is driving member. In case of this diagram, this is driving member, so observe the direction of rotation. In this case, this is clockwise direction, and mark tangential force which oppose this direction of rotation. So in this case, if we want to oppose this direction of rotation, so this is the arrow head. So this is the tangential force, and in case of driven gear, this is opposite. So in case of driven gear, if this gear rotates in anti-clockwise direction, then ft supports that rotation. So ft is like arrowhead is on left side. If we want to mark fa, that is axial force direction, then we discuss that in next point. First we discuss about the formulas. So tangential force Ft is equal to power upon pitch line velocity V, which is equal to torque on pinion upon radius of on pinion, which is equal to torque on gear divided by radius on gear. If we see the next force, that is formula, that is radial component or radial force Fr. If we calculate the ft force, then we can easily calculate this radial force. So Fr is equal to ft into tan phi t, where this phi t is transverse pressure angle. Fr is equal to ft into tan phi n divided by cos psi, because tan phi t is equal to tan phi n upon cos psi. Third force is thrust or axial force Fa. Fa is equal to ft into tan psi. And now we discuss about the direction, how to show this Fa. If we observe this diagram, if we observe this diagram again, so in this case Fa acts on left side or right side. So two options are there. So how to decide that direction? So for deciding the direction of thrust force depends on three different points. First point is whether the gear under consideration is driving or driven gear. So observe which is driving member and which is driven member. Second point is the hand of helix of gear under consideration. Which hand of helix is there? That is also important. Third is the direction of rotation of gear. Now we decide the direction of rotation. So if we consider this is the driving gear, observe which is driving gear. So if we consider this is driving gear, or find out which is driving gear and consider this rule for that driving gear. Now if this inclination is like this, then this is right handed, and for that purpose use your right hand. If the direction of rotation, if we observe from the left side, and if the direction of rotation is like this, then and this is right handed, so use your right hand, and this rotation is from upward to the lower side. So turn your fingers. If we consider this tip of the fingers is becomes the arrowhead, then you turn your finger like this, and at that location this thumb indicates the direction of axial force. So in this case direction of axial force is like this. So this is the Fa. Now we see the actual design procedure of helical gear. So if we see the the step first is beam strength calculation. So in case of helical gear, our FB formula is, that is beam strength. Beam strength is nothing but maximum tangential force acts on the gear tooth before the bending failure. That is FB is equal to sigma b into b into mn into y dash. So in this case sigma b is the bending stress. Sigma b is equal to ultimate tensile strength divided by 3, and this b is face width. B is greater than or equal to 1.15 pi into mn upon sin psi, or it is between the this range, that is 9 times normal module is less than or equal to b is less than or equal to 15 times of normal module. And for this y dash is Levis form factor, and for calculating this y dash is equal to 0.484 minus 2.87 upon z dash for 20-degree full depth involute. If 20-degree stub involute, then we use y dash is equal to 0.55 minus 2.64 upon z dash. For 14.5-degree full depth involute and composite, y dash is equal to 0.39 minus 2.15 upon z dash. So this is the formula, or this becomes the relation for calculating the bending strength. Now after substituting these values for pinion and gear, then we or sorry for substituting the values of this term sigma b, then y dash, because b and mn is common in pinion and gear, so the deciding factor becomes sigma b into y dash. So find out sigma b into y dash for pinion as well as gear, then compare these values, find out which is less value, and substitute for that value. That is, if pinion sigma b into y dash is less than gear sigma b into y dash, then here pinion is weaker, and then you substitute the pinion values in beam strength equation. So here, if sigma b into y dash for pinion is less than sigma b into y dash for gear, then pinion is weaker in bending. If sigma b into y dash for pinion is greater than sigma b into y dash for gear, then gear is weaker in bending. So here we finish our first step of gear design, helical gear design. And then second step becomes wear strength calculation. For wear strength calculation, this is the formula: Fw is equal to dp into b into q into k upon cos square psi, where dp is pitch circle diameter of helical pinion. Sorry. B is B is phase width, Q is ratio factor. If gears are externally connected like this, if this is the pinion and this, sorry, this is the gear and this is the pinion, and this is externally connected, then this is the formula: 2 times Zg upon Zg plus Zp. K is load stress factor, and that is depends on materials. For steel pinion and steel gear, then use K is equal to 0.16 into BHN upon 100 bracket square. For cast iron pinion and cast iron gear, use K is equal to 0.21 into BHN upon 100 bracket square. For steel pinion and cast iron gear, use K is equal to 0.18 into BHN upon 100 bracket square. Now third step is effective load calculation. So two different methods are there, that is preliminary estimation method. When the dimensions are not known, we use preliminary estimation method, and when the dimensions are available, then we use this second method for calculating effective load, that is precise estimation method. For effective load calculation, that is preliminary estimation method, this is the formula: F effective is equal to Ft max upon Kv, where Ft max is equal to Ka into Km into Ft divided by Kv, where this K is application factor, Km is load distribution factor, Ft is theoretical tangential force, Kv is velocity factor. This is the dynamic factor, that Kv. Then second method for calculating effective load is precise estimation method. Here F effective is equal to Ft max plus Fd, which is equal to K into Km into Ft plus Fd, where Fd is calculated by scientist named as Buckingham, and for calculating Fd, this is the formula: Fd is equal to 21v into bracket b into c into cos square psi plus Ft max into cos psi divided by 21v plus under root of b into c into cos square psi plus Ft max, where this v is pitch line velocity, b is phase width, C is that is load concentration factor, psi is helix angle. If we calculate all these terms, then uh, we can get F effective value. And after getting that F effective value, the last step is step 4, that is safety of helical. Check the safety of helical gear pair, that is safety against bending failure. If we calculate FB and FW, then compare FB and FW value, which is less. For that purpose, you use this equation. So if FB is less than FW, then your gear is weaker for bending, so use this equation, that is FB is equal to factor of safety into F effective. If we gear is weaker in wear, that is Fw is less than Fb, then use this relation, that is Fw is equal to factor of safety into F effective, and substitute all the values, Fw, F effective, and calculate factor of safety, and compare this factor of safety with available factor of safety. If your factor of safety is greater, then your design is safe, and then stop your calculation. And if factor of safety is less than available factor of safety, then you move to second trial and increase the module value, and again calculate all the dimensions. So how to calculate that module value, that depends on preliminary estimation method. In case of preliminary estimation method, so here in case of a preliminary estimation method, as here F effective, we substitute these terms in terms of module, and we use the same formula. So FB is in terms of module, F effective in terms of module, and factor of safety we substitute here, which is available, and by using this equation we get the module value. So in this way we can get the module. And here two f effective equations are available. So first f effective, that is preliminary estimation method, this effective load calculation, this equation is used for calculating the module. And precise estimation method, this f effective is used for checking the design, that is whether the factor of safety is safe or not. So for that purpose we use precise estimation method. So in this way, today we discuss the design procedure for helical gear. And here we finish our discussion. So thank you.